Hey, welcome to another Keymaster episodes. I'm Sven, and today I've got my good old buddy from Australia, Mr. David Hook. And we want to look at the insight into stateless PQC digital signatures. David, this is a very interesting subject that I thought we should talk about. So
hmm
first off, what does it mean for an algorithm to be stateless, and what are the differences in these algorithms?
So the first thing on the stateless nature, it doesn't mean they don't have a home. What it means is that if you look at the original two post-quantum algorithms that were recommended for usage, which was XMSS and LMS,
Oh,
they actually required the constant rotation of the private key each time you generated a signature. If you failed to do that, then what happened was the security of everything was compromised. This made things very difficult.
just a smidge.
Yeah, just a smidge. I mean, what we're used to is RSA and elliptic curve DSA and DSA, where, we just basically keep generating signatures, not too many, of course, but, more or less at abandon, and we don't have to worry about the private key changing. The new stateless algorithms, ML-DSA and SLH-DSA, actually also allow you to just maintain the private key stably and just keep generating signatures as you need to, up to 2 to the 64 signatures, which is quite a lot of signatures.
Yeah.
Yeah, so fairly safe to distribute across your network, have multiple servers doing it. I mean, there will be some applications, I'm sure, where they manage to crank out that many, but yeah, most of us will be quite happy with it, I think.
So what is the difference between a pure and a hash in the
Okay,
post-quantum here?
so yeah, one of the interesting things about these two algorithms is there's actually a pure ML-DSA and there's a hash ML-DSA, and there's also a pure SLH-DSA and a hash SLH-DSA. Now, the first thing with that is that the pure algorithms, as it's implied, kind of don't do any additional hashing except inside the algorithm itself. The ML, of course, for ML-DSA stands for Modular Lattice. So the signature is actually lattice-based and constructed that way. And then with SLH-DSA, it's actually built on I guess, again, a Merkle tree construct, very similar to what XMSS uses in the stateful one, but there's a bit of an intuition about how that tree is constructed, which allows you to generate multiple signatures. That also has a pre-hash and a pure version. The idea of the hash versions, it's to meet two situations. Like traditionally, if we were signing a message digest that was based around RSA, for example, you'd calculate a hash of the message and then you'd encrypt it using the RSA private key. Now, with ML-DSA and SLH-DSA in their pure mode, basically you have to feed the entire message into the signature algorithm. And one of the reasons for that is, some stuff gets prepended to it, and in the case of SLH-DSA, the message actually ends up being passed twice.
Mm.
So what happens there is that, of course, if you're in a situation where you either don't have access to all the information that's required to be prepended, so an example is the public key, or you're dealing with a signature device which can't support the message size you've got, you actually can still calculate a hash. So the pre-hash modes are defined to use SHA-512 and SHA-512 only. And the idea of those is to fill in that gap where there's either a lack of public key or you actually need to actually just calculate a hash first and then actually get the algorithm to sign that.
So what do you do? Is there, I guess what I'm trying to say, is there an alternative to pre-hash for ML-DSA for, like, I have a constrained HSM. Like, let's say I have an HSM that could only handle signing of a 16 kilobyte message.
Yeah, okay. So there is, as it turns out. Initially in the FIPS standard that looks after ML-DSA, which is FIPS Pub 204, there's actually this kind of throwaway line in the signature algorithm where it goes, this could be done externally.
Oh,
Where
externally.
they're talking about the calculation of move. And I guess it's kind of an academic discussion now what was originally meant when that comment was included, but what has happened after negotiation between a number of parties, including NIST and also the IETF group that are trying to standardize the use of ML-DSA for PKI and things like that, is that it's been decided that you can do the external mu calculation. And what that essentially means is that in ML-DSA, you can actually take the prepended information as the public key and everything, and then you add your message, you calculate the hash from that, and then you can give it to the next stage of the algorithm. So the next stage of the algorithm in ML-DSA is actually about signing this mu value. It's that next step in computation. So for your constrained HSM case now, like if you're trying to do something like sign a 100 megabyte CRL or something like that, rather than having to use hash ML-DSA, you could actually use external mu. And so do the mu calculation on your client on the CRL, and then pass the mu value, which is just 512 bits, to the your actual HSM, which you can then sign using the external mu calculation internally and give you back a proper ML-DSA signature, which will verify on anything that's using pure ML-DSA.
Wow, that's really good that they put that little external option in there.
Yeah, no, I think everyone was very happy with that particular outcome.
Yeah, that could have been
especially us implementers.
Pretty complicated if it wasn't.
yeah. No, the idea is good. Yeah.
So is there an equivalent to external mu for SLH-DSA?
Unfortunately not. Due to differences between the two algorithms, you can't really pull the same trick with SLH-DSA. But, you still have the hash version of the algorithm available if you actually need to sign something that's too big to pass the HSM. But you'd have to be generating a hash ML-DSA signature for that.
Okay, so yeah, the pure is really the only limit then, or the hash. If you were limited where you had to use pure, you couldn't. You'd have to use hash. Is what I meant. Yeah.
So there's something like CMS, for example, where we use signed attributes in that term, and it's not really a problem because the hash is usually embedded in the signed attributes. So there's a lot of situations you should be able to get around. It's just things like, if you're trying to direct sign a very large CRL, it can be very inconvenient.
Yeah, that would not be great.
No.
Anyhow, that's a little insight into some stateless PQC digital signatures. We hope you found that fun, and we'll see you in the next episode.